Okay, so all these problems are kind of the hardest part, I think, um, about these optimization problems. And so none of these even really talk about optimization, but you're basically doing optimization without really knowing it or without having to know it. So, okay, so the first thing is we want to find a formula for the sum of the squares of the two numbers. Okay, so always come up with variables. We'll call the two numbers x and y. Okay, that means the sum of the squares of the two numbers, the sum of the squares of the two numbers. Okay, then we always want to get this in terms of one variable. So they'll give us extra information either in a form of a sentence, or it might be in some picture that they give. Okay, so they say the sum of two non-negative numbers is 20. Sum of the two numbers is 20. Okay, so we can solve this for either one and then plug it in. I'm going to solve it for y. Just subtract x. Okay, then we'll take this and substitute that in for y. Okay, so now we have what we want. So it's a formula for the sum of the two squares in terms of one variable. So that's the main thing that we want to do every time. Okay, now we'll let's clean this up a little bit. Okay, just to do this quickly, this will end up combining. If you FOIL that and combine like terms, you should get this. Okay. What am I doing? Okay, so now I just graphed it. Take a look at the graph. So kind of points that we're focused on if we were doing optimization. Do you see this is a minimum? And then if we think about the relevant domain of this, the fact that you're adding two non-negative numbers to be 20, it means either one of these numbers can't be bigger than 20. You know, our sum formula deals with x here, and we can see like this x can't be bigger than 20 because that would force y to be negative, and y can't be, you know, neither one of these. Okay, so the relevant domain would be from 0 to 20. Okay. And then the formula, let me put the formula here. Okay, and then we also want to find critical values. So let's do that. So we'll take derivative. And then set it equal to 0. Okay, we get x is 10. And then just have that confirmed. You see how what we really found is the x value of this minimum point. Okay. And so we're just kind of noticing that for now. And that's it. Okay, the next one says find a formula for the sum of one number and the square root of the other. Okay, so we're using the same kind of extra information where the two numbers have to add up, two non-negative numbers have to add up to 20. And they say find the formula for the sum of one number and then the square root of the other. Okay, so we're going to do same thing, solve the extra one for one of the two, doesn't matter which one. I'm going to solve this one for, what's better? Doesn't really matter. I'll solve this one for x. And then we'll plug this in for x over here. Okay, so that's our formula. It's in terms of one variable. So let's write that down. 20 minus y. And then plus root y. Okay, so relevant domain. We know it's definitely 0 to 20 just based on this. And that's it. You know, the square root has to be positive, but it's already stated that they have to be positive, so that doesn't matter. Okay, so relevant domain is the same as the last one. The smallest it could be is 0, and the biggest y could be is 20. Okay, so here, let's graph it. Okay, so there's a graph. If you graphed it, you'll see there's a little, whoops, there's like a little maximum there, it looks like, just after, you know, at 0.25. Okay, so. All right, so now we're going to, what's next? Oh, find critical points. Okay, so let's do that. So take derivative. So -1 plus 1/2. You know, this root y is y to the 1/2. Okay, and we'll set this equal to 0. Okay, and I'm going to take reciprocals of both sides. You can do that. Okay, and then we can see 1/4. If y is 1/4, we square both sides really. So y is 1/4. Okay. Okay, and then look at this point here. Do you see you know, these are y. This is a y value technically, and this is an s value, the sum. Okay, so just notice that the maximum value happened at that critical point. Okay, next one, find a formula for the perimeter of a rectangle whose area is 16 square inches. Okay, so we'll draw a box. Let's see if I can draw a box. That worked. Okay, so we'll call that x, and I'll call that y. Okay, we're finding a formula for perimeter, for the perimeter. So we'll do perimeter equals 2x plus 2y. So don't worry about how many variables it's in to start with. Okay, they say the area has to be 16. Okay, so that has to be 16. Solve this for y. And then plug it in for y. So 2 times 16 over x is 32 over x. Okay, so that's our formula for the perimeter. Okay, so let's graph that. Actually, sorry, let's think about the, before we graph it, let's think about the relevant domain. And then once we see the graph, it'll make sense. Okay, so relevant domain, really these, you know, this x is this side. So this side, the smallest it can be is 0. You know, it can't be 0, but, you know, we'll do parentheses 0. It can be anything greater than 0. And it can really be anything. It could be infinite, you know. You could have this x could be something really, really big, like 1,000,000, and then just y is like 16 divided by 1,000,000, you know. Just need, you know, something that y would be something really small, close to 0, just to make sure that they multiply to be 16. So really this can be as big as we want it to be. So go to infinity. Okay, so we'll look at the graph now. All right, so you should get a graph like that. I remember we did this in class, and hopefully everyone sees how to rescale in Desmos. If not, this graph will look really flat and you'll barely see a minimum. Okay, but look at the minimum. So 4 comma 16. So the minimum happens when x is 4. So let's see. So now we'll take critical values. So take derivative, or find critical values. Take derivative. Remember, this is 32x negative 1. So take derivative. Okay, set this equal to 0 to find critical values. If we do, we'll get x to the negative 2 equals 1 over 16. That means we can take reciprocals of both sides, so x squared equals 16. So technically x will equal plus or minus 4, but it can't be negative, right? If we look at the domain, it just equals 4. Okay, notice that was the x value of the minimum point that we can see from the graph. Okay, and this one, find a formula for the area of the rectangle shown in the figure. Okay, so first off, this one's a little trickier maybe. So every point can be considered like x comma y. All right, so if this point is x comma y, that means you go over x and up y. So this distance is y, and this distance is x. Okay, so if we're going to look at the area of this, we can say it's length times width. And if we call this the length, then if this is x, the whole thing is 2x, since there's some symmetry. Okay, if we call this the width here, then this is just y. Okay, so we got a formula for the area of that rectangle. Now we just need it in terms of one variable, so we'll have to get an extra equation that involves x and y. Okay, this this point here, the direction should have said it. I kind of got these from books but didn't do the whole directions. But this point has to be on this line here. A little bit of geometry will show you that this y-intercept is 1 and the slope is negative 1. So the equation of this line, call this line L. The equation of that line L is y equals negative x, since the slope is negative 1, plus 1, because of the y-intercept is 1. Okay, and then if that's y, we can take this and plug it in for y here. Okay, I'm going to simplify that a little bit. Okay, now relevant domain. So our formula is in terms of x, and x is this distance here. So in order for, this point has to go on this line, but it can't go to the left here, because then if the point's up here, you can't really create a rectangle. A rectangle is created by going down to the x-axis and over to the y-axis, or over to the other side, I guess. And that's what creates the rectangle. So if this point goes to the left of the y-axis, you can't really do that anymore. Or if it goes to the right of the y-axis, you can't really create a rectangle anymore. So really the smallest x could be a 0. It has to be greater than 0. And it really has to be less than 1. negative 2x squared plus 2x. Okay, so let's graph that. Okay, so see the point of this relative max on the relevant domain is at 1/2. Okay, so that should be our critical value. So let's see if it is. Okay, so we take derivative. Okay, and then x does equal 1/2. Okay, so that x value is the x value of that relative max, and really absolute max on that interval. Okay, next one, open top box is formed by an 8 by 15 inch piece of from an 8 by 15 inch piece of cardboard by cutting congruent squares from the corners and folding up the square. Okay, I did a kind of the tougher one in class, I think. So here, let's see. There's a rectangle. Okay, and then, whoops. Okay, and then we're going to cut out little squares. Let's see how to do this. Okay, so we're going to cut those out, and so these will, this will be empty here. These will all be empty, and these cuts are all cut of x. Okay, so hopefully you can see that you'll have like these, this is like a little flap here that you'll kind of fold up. You'll fold up the corners, and that this will end up being the height of the box. Same thing, this will be the height of the box because this little flap will get flapped up, all these little flaps here. And it'll be an open top box. Hopefully you can see that also. Okay, so we want to find a formula for the volume. Oh, that's a mistake. Sorry. Okay, it doesn't make sense finding the area of a box unless it's surface area. Okay, actually maybe that is it. Okay, let's do that. Normally it'll be volume, but we'll do the area. All right, that's okay. I'm gonna do volume. Sorry if you did area, but I'm gonna do volume. Area is not even interesting because really just make the smallest cut possible. That'll be the smallest area, or that'll be the largest area. All right, so for volume, so just start off with volume length times width times height. All right, kind of stuff that helps me is just looking at the bottom. If you're talking about one of these box questions, look at this is the bottom of the box, so that means like this will be, let's say, we'll call this the width, and we'll call this the length. So it's kind of easy to see, like when you have the bottom of a box, it's easy to see the length and width. Okay, and then think about, it's an 18 by 15. So this would be the 15 one, or 8 by 15. This would be the 8 side. Okay, and then if this whole thing is 15, and from this side we're cutting out 2 x's, that means the width is going to be 15 minus 2x. Same thing, if this whole thing is 8, and we're cutting out these 2 x's, then this length is 8 minus 2x. 15 minus 2x. And then the height, I don't know if you can imagine, like if we're looking at this flap, once you flap it up, this ends up being the height. So that's just x. Okay. All right, so if we FOIL all this out, we get that. We get minus 60x minus 32 minus 92. Okay, and then 150. Wait, 120x. Okay, and then let's look at the relevant domain. You know, definitely x can't be 0, or else we wouldn't create a box. So the smallest this could be a 0. Can't be negative because the lengths can't be negative. And then notice that like the cut can't be 4, because that means you'd have this cut that would like cut here, and then there wouldn't be a flap here, because you'd be, you know, you need to have, it has to be a little less than 4 to create even a little flap here. I don't know if you can imagine that. Another way to look at it is this here is the length. So this has to, you know, you have to pick a value of x that makes this positive. You know, so if this x is bigger than 4, then this length ends up being negative, and that won't make sense. Same thing here. So this length would have to be less than 7.5, but you always kind of look at the smaller one, you know, the I guess less inclusive one. So really, x can't be 4, but it can be anything less than 4 as long as it's positive. Okay, so let's graph it on that relevant domain and see what we have. Okay, so first off, I made a mistake. This should be 46 instead of 92. Okay, and then that's what I graphed. Okay, so we look at that, graph that on the relevant domain from 0 to 4. And you know, there's a lot more to this graph, but we only can pay attention to this part of the graph, right? Because this function doesn't apply when x is greater than 4 or when x is less than 0, because we have this real world situation. Okay, so let's take derivative and see what the critical points are. See, 6 goes in there. Okay, so this 3. And then that'll be, whoops, not 3. That's 4. 4 goes into all those, yeah. That'd be 23x, I think. 23, yeah. 30. Okay. Okay, so now we'll set this equal to 0. We'll do box method, or whatever, factor by grouping, however you want to do this. Okay, so that's minus 5, minus 18. Okay, and here we get, oh, whoops. And then I'm doing this divide and slide thing. I don't know if y'all have done this. So divide by 3, divide by 3. And then this is really 3x minus 5, x minus 6. Okay, so that is same as this. Okay, and then, so, you know, if we set each one equal to 0, we get x equals 5/3, and we get x equals 6. X equals 6 we can ignore because the relevant domain only goes to 4. And then 5/6 is 1 2/3, which is 1.6 repeating, and we can see that's the x-coordinate of that absolute max on that interval. Okay, actually, let me write the formula. Okay, and obviously this will be different than what you got, but the area one's not interesting, I think. Okay, next one, regular rectangular plot of farmland will be bounded on one side by a river and on the other side by 800 meters of single-strand electric fence. Okay, so let's draw a picture. Okay, so, you know, it's going to be bounded on one side by some river. So we'll say there's the river. And then on the other sides by some fencing. And it's a rectangular plot of farmland. Okay, so that's just an example of one possible rectangular plot. Okay, we'll call, I don't know, call that x and call that y, and we want to find a formula for the area of this. Okay, so first thing's easy, area of that rectangle. And then now they say that, you know, this is the strand of electric fence, and this has to be 800 meters long, and so really we'll get 2y plus x equals 800. Okay, and then solve this for either one. I'll solve for x so that we don't have fractions. Plug that in. Okay, and then plug that in for x. And then simplify. Okay, relevant domain. So, you know, x and y each have to be positive. That's the main thing. Can't be 0 or else there won't be a rectangle. And then, you know, the x could go up to 800. You know, it can be anything up to 800. And that means y would end up being really small. So the biggest x could be is 800, but this y is what we're dealing with here. So this y can't be bigger than 400. It can't be 400 or bigger. You know, if this y was 400, this would be 800, and x would be 0. So we can't have that. This length can't be 0. If y is bigger than 800, or bigger than 400, that would force x to be negative. So that y goes to 400. Now, if you did it a little different, if you solve for y, or you called this, really, if you solve for y, actually, then your domain might be different. Your domain might be 0 to 800, depending on, I think. Yeah, actually, I'm not sure. Anyways, okay, so let's graph. Actually, I'm going to put this formula. It should be squared. Okay, let's graph it. Okay, so we see there's the graph there. There's that the coordinates of that relative max, or really absolute max on the interval. Notice the interval is from 0 to 400, and that's this interval where this is above the x-axis, which makes sense because this value, and really any y value on here, represents the area of that rectangle for that given x value. Okay, so let's take derivative, see if we can confirm our critical value. That equal to 0, and we do get y is 200. And that is, this is a y coordinate and an area coordinate. And that confirms our y coordinate was 200. That's it. Okay, next one, find the formula for the surface area of an open-top square-based rectangular steel tank whose volume is 500 cubic feet. Okay, if we want to draw a picture, we can. So here I'm going to draw a picture real quick. Okay, so that's a square base. So here I'll show you how my sister did it. She's an art major. Okay, that'll be the height. That'll be one of the dimensions, and it's a square base, so the other one should be the same. Okay, and then just draw these lines parallel. Equal size. Okay. Square, so I'll call those each x, and I'll call that y. Okay, so we want a formula for surface area. Okay, surface area. Okay, the surface area, and it's an open top box, so we're not, there's no area here. So we're just finding the area of the front and back, the two sides, and then the bottom, and adding that all together. Okay, so the bottom is x squared, the area, and then the area of every other face is x times y, and there's 4 of those, so 4xy. Okay, then they say the volume has to be 500, so just multiply all the dimensions. That's the volume, and that has to be 500 exactly. All right, we'll solve this for either variable. I think it definitely makes sense to solve for y. If you solve for x, you'd have square roots, plus there's 2 x's in our surface area formula. So definitely solve for y. And then we'll plug it in for that one y there. Okay. Okay, we get that. Okay, relevant domain. So ours is in terms of x, so ours is in terms of the dimensions of the bottom. Definitely has to be bigger than 0. And then I don't know if you notice that x can really be as big as you want. The only constraint is that the volume has to be 500. But x could be super big, and then y would just be super small. Crazy small height for as big as you want for the base to be. So really this could go, that x value could go to infinity, and there's nothing stopping that. Okay, so let's graph this on the domain. I'll go as far to the right as I can to capture the relevant domain. Okay, so there's the graph. You can see that 0.10 comma 300. Let's see if we can confirm that we'll get the same thing. Really, 10 should be the critical value. Let's see if it is, or one of the critical values, if there's more. Okay, so we'll take derivative 2x, and this is 2000. Okay, set that equal to 0. You can do this a lot of different ways. I'm gonna add this to both sides and then change it. So I will get 2x equals 1000 over x squared. Maybe divide these by 2 times by x squared. And then that means x equals cube root of 1,000, which is 10. Okay, and then that's, yeah, so that's the x value that we got. So we kind of just confirm those. Confirm that. Next one, find the formula for the surface area of the paper used in a poster, which has 4-inch margins at the top and bottom, 2-inch margins on the side, and contains 50 square inches of print. All right, so if this is the first time you've done one of these, then yeah, here, I'll just kind of do it. Okay, so there's the paper, and then that's the poster, and then there's 4-inch margins at the top and 2 on the sides, so it'll be something like this, like that. Okay, and then so the inside is where the print is, and the outside is the margins, right? Okay, so just keep in mind, like, this little distance here is 2. This distance is 2, which means this distance is 2, and then this distance is 4, just like this. Okay. So we really need to figure out variables. So the one question is do we call x the outside part or call x the inside part? I think it doesn't matter, but I'm going to call x this inside distance. Can't remember if it matters, but okay, so I'm going to call like this x and this y for the inside part. Okay, so they say find a formula for the surface area of the paper used, so for the whole thing. So if I'm just calling x this, that means this whole dimension down here is really 2 plus x plus 2. So really this whole thing is x plus 4. Same thing, this whole thing is going to be y plus 8. Right? Just this alone is y. That's 4 and that's 4. So this is y plus 8, the whole thing. Okay, so that means this area is x plus 4 times y plus 8. Okay, and then they say that the printable area is 50. So that's this area where the print is going in this poster. These are just the margins on the outside. And that has to be 50, so x times y is 50. Okay, so we'll solve this for, I'll solve it for y, and then plug it in. Okay, and then let's FOIL this a little bit. Okay, 50. Okay, actually, I'll do one more. Okay, so let's graph that. Oh, actually, before we graph, let's find the domain. Let's do that first. Okay, so this is in terms of x, so we can see this value here. this this x has to be greater than 0 for sure. Okay, and then this area has to be 50, but with area there's kind of no restrictions for how large something can be, because then the other one could just be super small. And so really this just goes to infinity. Okay, so now let's graph it. Okay, so let's see that minimum. Okay, let's find critical points for this one. Take derivative. Okay, right, yeah. Okay, so we'll set this equal to 0. Okay, so we'll minus 8 divided by negative 200. And then that simplifies by 125, so that's 1 over 25. So really 1 over x squared equals 1 over 25. We can see x is plus or minus 5, but really 5 since it has to be positive. And we can see that's the x coordinate of that absolute minimum value. Okay, next one. Find a formula for the area of a triangle whose side lengths A and B, with side lengths of A and B, and whose angle between the sides is theta. Okay, so we'll draw just any triangle, doesn't matter. Okay, call that A and B, and the angle between those sides is theta, so that's theta there. Okay, so there's a formula for this. I don't know if anyone looked that up. It's 1/2 AB sine theta. Oh, there's no constraints on this one. Oh, I don't know. I must have made a mistake. You can't do this one because you can't get it in terms of one variable. Alright, so this is a mistake on my part. I must have just forgot to put the constraint in there, or that extra information in there. And if that ever happens, you can't solve these. So there's, yeah. Okay, number 9. Find a formula for the surface area of an open top right circular cylindrical can that can hold a volume of 1,000 cubic meters. Okay, so basically just talking about a cylinder. Okay, and it's an open top, so no top here. And it can hold a volume of 1,000 cubic meters. All right, so let's call, since we're dealing with a we have like a cylinder, we'll want to talk about the radius of the base and then the height of the cylinder. All right, and then so volume for a cylinder is pi r squared h. So the area of the base times the height. Okay, so that's, and then that has to be 1,000. Okay, so actually I started with the constraint formula first, or constraint equation first. Usually you'll start with the other one. Okay, find a formula of surface area. Okay, so surface area. So surface area is, if you have a uniform solid, it's perimeter times height. And here perimeter of the base times height. Perimeter of the base is circumference. So it's 2 pi r h. So that'll be all the area around. That's lateral area, they call it. Okay, so surface area is 2 pi r h. And then plus the area of the bottom. And there's no top, so just the area of the bottom is pi r squared. Okay, so if you didn't know that, hopefully you looked it up. Real easy just to look that kind of stuff up. Alright, so now we're going to, I'm going to solve this one for h, this equation here. So that's just 1000 divided by pi r squared, and then substitute it in for h here. Alright, then we'll clean it up a little bit. Okay, relevant domain. So our domain is now in terms of r. So definitely that's the radius of the base. Can't be negative, can't be 0. If it was 0, you wouldn't have a cylinder, and this probably wouldn't make sense. And lengths can't be negative. Okay, yeah, same as kind of all these. Volume doesn't really bound stuff, variables from above. So this can go all the way to infinity. Okay, so let's graph this. Okay, so there we can see what the minimum value is and where it occurs when r is 10. So let's see how that works. Okay, so take derivative. Okay, set that equal to 0. Okay, I'm gonna divide everything by pi. Those pi's cancel. Divide everything by 2. And I'm gonna multiply everything by r squared also. So then if you multiply this whole thing by r squared, it'll cancel out with that r to the negative 2. And just get that. And we can see r is 10 here. Okay, was that what we had? Yeah. Okay, so that's the x value of that minimum. Okay, this is one we did in class. I'll kind of go through this quickly. Ultimately, it says find a formula for the volume of the box. Okay, so volume of a box just in general. Length times width times height. Okay, so this, if we look down here, this is x, and then like halfway that's x and that's x, and then that's x like that. And then up here, like that distance will be x, and then this distance will be x also. Okay, so if we want to, so look at this, the base, this is the base of the box. So we know like one of the dimensions is going to be 2x right there. Let me see the whole thing. Okay, yeah, so that'll be 2x. So keep in mind this is the base. Oops, I'm going to do that in red. So here's the base down here. And that'll be like length and width, you know. So nice to kind of focus on that. Okay, so we can see whatever that dimension, one of these dimensions is 2x. Okay, so let's get this dimension here. Okay, so if you see this whole thing is 24, and that's x, and that's x, so this length is 24 minus 2x. Okay, so let's write those. 2x, 24 minus 2x. Okay, the height's kind of weird. So the height is really this distance here is the height. So hopefully you can see that when just the way that this works. If you like take this, if you like fold this flap up, you know, up like this way, kind of. I don't know how to say that. And then really this whole flap here kind of becomes this. Like when you fold it and then fold it up, it'll become like that kind of, and that'll be like coming straight up. I don't know, it's really hard to explain in this thing. I don't know. Okay, so hopefully people see that. So really it's it's this distance, that's the height. All right, and then this whole thing is 36. Yeah, so it's like this whole distance is 36. And then this is x, 2x, and x. So if we subtract 4x, we'll get these two lengths together and then divide by 2. So you could say the height is 36 minus 4x. That'll give you the sum of these two, and since they're both the same, divide by 2 to get one of them. Okay, another way to do it is call each of these lengths h, and then just set up a little equation. Say 2h plus 4x equals 36, and then solve that for h, and you get the same thing. Okay, so relevant domain. Actually, let's simplify this first. Okay, so that's what it ends up being if you simplify it. All right, relevant domain. So x is one of those cuts that you make. You can see kind of, you know, the length is this, the width is this, and this is the height. So each one of these really has to be positive. And so we definitely, x can't be 0, but it can be anything greater. And then, according to this, x can't be bigger than 12, can't be 12 or bigger. And according to this, x can't be 9 or bigger. So really, x can't be 9 or bigger. So 9 will be the biggest that it can be. So that's our relevant domain. Okay, so let's graph this now. Okay, so for this one, and one thing I made a mistake, that should be a 1. Whoops, damn it. Okay, that should be 168, and that's what I graphed. Okay, fix this. Okay, so we can see the relevant domain. Makes sense that it's only the part where the graph is above the x-axis, because all the y values of every point on this represents a possible volume. So we want to only consider when the volume is positive. So, all right, if we took the derivative of this, let's take derivative. All right, and then, you know, this I think we'd have to do quadratic formula for. Yeah, we can see that x value is kind of a weird decimal. So maybe you can do it in your calculator and just make sure that if you set this equal to 0, just make sure that one of the two x values is that 3.94. Actually, I'm going to do that kind of quickly here. Okay, so, oh my god. So I did that in Wolfram Alpha. So I did just typed in that equation equals 0, and these were the two zeros, 3.394, and that's the x coordinate that we got. I think there was another minimum if you looked at the graph kind of right around here, a little bit more than 10, and that makes sense. The other critical value is really a minimum of the whole function over here, but we're not really interested in that part because we can't pay attention to that because this part doesn't make sense. Just like we can't pay attention to this part because it doesn't make sense in the context of this. Okay, next one, find the formula for the area of a rectangle, which is inscribed under the arch of the curve from there to there. Okay, so I'm going to do a picture in Desmos. Okay, so they talk about a rectangle that's inscribed. And so really if you just pick any point, doesn't matter, pick any point on here. I'm just picking a random point now. So just pick this point. And then now you can kind of create a rectangle based on that. Kind of like we did another problem. That was like that. Okay, and this should be symmetric. Actually, let me make sure this is symmetric. All right, and then this is the rectangle that we're looking at. Okay, and then we want a formula for the area of this rectangle. Okay, so this point is x comma y, but then that y is 4 cosine 0.5x. Okay, so technically this is x, just that distance, and then this whole distance here is y. So really 2x, because that's x also. So the bottom is 2x, and the top is y. But then we have, this point that's like one of the corners of this really has to be on this curve. So the constraint is forcing that y coordinate to only satisfy this function that was given. And so really that is our extra equation, that function. And that's real typical that whatever graph or function that you're given, if this is in a coordinate system, whatever graph you're given, if a point is forced to be on there, then that's like a constraint. And you want to use constraints in these problems. All right, so we'll substitute for y. So we'll use, okay, and then we'll clean it up. Okay, so let's graph this in Desmos now. Oh, sorry, let's find the relevant domain. Okay, so this x value, the way I did it, the relevant domain really bigger than 0. If it's less than 0, you could still make a rectangle, but it would just be a little different one. So let's just say bigger than 0, and then this distance has to be less than pi. Right? If it was pi, then you wouldn't be able to create a rectangle, and then greater than pi, and it wouldn't make sense. So this is really just from 0 to pi that will be interested in this graph. Okay, so let me grab that graph from Desmos. Okay, so there's the graph of our area function. Okay, so I don't know what that 1.721 is. Maybe that's square root of something. Actually, let's see. All right, so let's find critical values by taking derivative and setting equal to 0. or figuring out where it's undefined also. But okay, so here we have to do product rule. I'll consider this to be one thing and this to be the other thing. So derivative of the first thing times the second plus first thing times derivative of the second. Derivative of cosine is negative, so this will be minus. And then 8x really times 0.5 because of the chain rule. And this will be this. Okay. Okay, so this you really have to get a calculator to solve. Okay, so this, yeah, so really just this you'd solve in your graphing calculator. So I'll do that real quick. Let me do that. Okay, so I did it in the graphing calculator. Oops. And you can see that that 0 is 1.72, whatever, just like it should be. So the 0 of the derivative was so this is the derivative that I graphed. So that's the 0 at 1.72, whatever. So yeah, so that's one of the critical values. And we can see at that critical value there was an absolute max on this interval. Should make this a little bigger. Oops. Oh my god. Oh my god, stupid. Okay, final formula for the volume of a right circular cylinder inscribed in a sphere of radius 10. Okay, so hard to draw on this. Actually, I'm going to get a picture from the internet. That'll be better to see what's going on. So we want a cylinder inscribed in a sphere. Okay, so find the formula for the volume of a right circular cylinder inscribed in a sphere of radius 10. Okay. So we have to get a formula for the volume of that cylinder. And so we'll start off with that. So whoops. Volume is pi r squared h. Okay. So, but then now we need to get in terms of one variable, and and keep in mind when this r is different than the radius of the sphere, right? This little r is the radius of the base, one of the bases of the cylinder, but the radius of the whole thing of the sphere is 10. Okay, so watch how we'll kind of do this. So let's say that's the center of the sphere. So we can draw a line to a corner, of the cylinder, which is really this will be a radius of this. So that's 10, that distance. And then from the center of the cylinder up there, we can draw a line down and then a line over. This is a right angle. And then this here is that little r in our formula. And then the height of this whole thing is h. So this you can see is half that. So this is really h over 2. All right, so that's probably tricky to get that. And then now we can do Pythagorean theorem to get our extra equation that we'll use to substitute in. And I'll show you a couple one nice thing you could do. Okay, so Pythagorean theorem, r squared plus h squared over 4. Okay, so we could actually just solve this for r squared, since we have an r squared over here, and then substitute that in. Okay, and then now we'll just substitute that. Okay, r squared is that whole thing. And then times h. Okay, so if we, whoops, that was weird. Okay, so if we distribute like the pi and the h, we'll get 100 pi h minus the, oh, whoops. Oh no. I'm going to write it like this. Pi over 4 h cubed. Okay, so there's the formula. That's good. In terms of one variable. Okay, the domain, so that's a height. It's a height right there. We can, so that height, smallest that could be is 0. Yeah. And then the biggest it can be is really, so if this distance is 10, I don't know if you can think about this, if this base gets really smaller, this radius gets smaller and smaller, then this, half of this height gets to be, half of the height gets to be closer and closer to 10. So really the height can't be bigger than 10. This whole height can't be really big, bigger than 20. Can't be bigger than 20. So hopefully you see that. Okay, so let's graph this, just paying attention to that domain. Okay, so there's the graph. Let's take derivative, see what happens. Okay, set this equal to 0. Pi's cancel. And you get h squared has to be 400 over 3, I think. 400 over 3. And that means that h has to be technically plus or minus, but really just positive. Really 20 over square root 3. Okay, and then if we do that in the calculator, that must be, here, let's do that real quick and make sure. Yeah, so I just did that in the calculator, and that is 11.5470538. Okay, and that's how they got that x-ray. So that was the critical value that we were looking for. Okay, last one. A rectangular sheet of paper with dimensions x and y and a perimeter of 36 is rolled into a cylinder with no top or bottom. So just a sheet of paper, you just roll it into a cylinder. Find a formula for the volume contained within the cylinder. Okay. Okay, so let's start off with the sheet of paper first. Draw that. Okay, sheet of paper has dimensions x and y. And the perimeter is 36. Okay, but they want us to find a formula for the volume. So we just imagine if we rolled this into a cylinder, kind of a wider cylinder than that though, I think, but I'm not sure, maybe not. Okay, if we can see the height is still y, but now this whole length got rolled up and now becomes that circumference. So here, really that circumference is x. So that means if we want to find the formula for volume of a cylinder, we can start there. So volume of a cylinder, pi r squared h. Okay. And then if we look here, if this radius is r, then really the circumference is 2 pi r, but we know that that's really x. So x equals 2 pi r. Yeah, so that'll be our one of our formulas that we'll use. Sorry, I'm just thinking. And then the perimeter is 36. So really 2x plus 2y is 36. All right, and then that means that x plus y is 18. I need that. All right, so now we have to substitute in to get this all in terms of one variable. So notice that we have this involves x and this involves x. So if you see, we know that h is y. So, and then the radius, now we want to get the radius in terms of y. Okay, and then this will be a little trickier, so here I'm going to kind of do it over here. So this means we can solve that for r. That'll be x over 2 pi. And then we can solve this down here for x. So x is 18 minus y. And then plug that in for the x here. Okay, and then that's what r is. And so we can substitute that now. So volume is pi times that whole thing squared, 18 minus y over 2 pi squared times h, which is y. Okay, so let's simplify this. Okay, pi. Okay, if we square the top, we get 18 squared, which is 432. Okay, so this y will cancel with one of those y, or pi will cancel with one of those pi's. And then I'm just going to write it like this. I'll pull out that 1 over 4 pi, and then just times it by the rest. Put it in order. Alright, so that's our volume formula in terms of one variable. Alright, so y is this height here. So it looks like y could be as small as we want it to be, but positive, so, and not non-zero. Or else we wouldn't have a rectangle, and then we couldn't create a cylinder. Okay, also, you can look at either one of these. You know, r is 18 minus y over 2 pi, or just x is 18 minus y. So you can see this y value, which is what our formula is in terms of, can't be bigger than 18. Can't be 18 or bigger, or that would make x negative, and we can't have this side length of that original rectangle be negative. So 18 is the biggest it could be. Okay, so let's graph that on that domain. Okay, so we can see that critical value over there, or that the x value of that maximum point. We can see first off the domain 0 to 18, like we said. That's the part where it's above the y-axis, x-axis. The x-coordinate is 6. It's really our y-coordinate, or kind of y value in this formula is really that x value. And if we took the derivative, oh, one thing I made a mistake. I know I make mistakes, but I graphed it right. That should be 324. Okay, so we'll take derivative, set it equal to 0. Okay, let's do that. And this constant won't matter since we're setting equal to 0, but I'll just still write it. Okay, so times everything by 4 pi, divide everything by 3. Okay, and then just factor that. 9 and 12. Wait. 6 and 18. Okay, so we can see y equals 6 or y equals 18 will be our critical values. Okay, and you can kind of see the significance. The 6 is the relative, there's the absolute maximum, and the 18 relates to the absolute minimum in this case. So each of those had meaning to them, and every critical value is going to have some meaning like that. But you know, we won't pay attention to the at 18 part because that's not in our domain. Okay, that's everything.